all of the systems we work with here at KS Analytical Systems produce ionizing radiation. This is in the X-ray spectrum, obviously, and it does require some special safety considerations. Exposure is a serious problem. In my experience, we've never had a recordable dose rate from one of these instruments that wasn't the result of some other type of mistake. And even then, it's extremely rare to see any type of recordable dose rate on a film badge, dosimeter, anything like that. The housings are very well designed. The safety circuits are very well integrated, and for the most part, they are foolproof and fail-safe. So today I'd like to go over some of the safety features that are fairly universal for the different instruments that we work with. The D500 and the D5000 are very similar. When we get into the XRF instruments, they're much more compact, they're much more integrated in that the user very rarely goes anywhere near the beam path of an XRF spectrometer, so they very rarely experience anything that has to do with the safety circuit. However, on the X-ray diffractometers, our users are constantly interacting with the sample area, which is directly in the beam path. The D8 diffractometers, Series 1, Series 2, A25, those become a little bit different, but the general principles are very, very similar. So we're going to go over the D5000 because it's convenient, it's right here, and it's pretty much the same, very indicative of all of the other systems. These principles even apply to other instruments across the board. So while there will certainly be some differences, the general idea of how these interlocks are applied is very similar. So before we even get into interlocks, let's talk about the shielding. So on a system like this is a theta D5000. We have our emission area over here. We have our tube stand, which you may or may not be able to see over on this side. The upper panels are all made of a thick gauge steel. That includes the front panel. If you ever remove one of these versus removing one of the lower panels, you will notice that the uppers are much thicker, probably about twice as thick. And that is for X-ray protection. The frame and the joints all have overlapping steel members. So none of this is, there is no direct line of sight into the instrument. We have an emission source here is the X-ray tube. It's like a light bulb, so as soon as we remove power, there is no emission at all from the X-ray tube. It's much different than a radiological source. It's regulated much differently. And in a lot of ways, it's much safer because when we remove power, we completely discontinue any ionizing radiation emission. So these are relatively easy to regulate. Now, as far as additional shielding, we have the thick panels, the overlapping joints, and then on our right side of the diffractometer, where theoretically we could have more of a direct beam or more scatter striking it directly, we actually have a superfluous inner panel that's just as thick, made of stainless steel, just as thick as the exterior panel. And then sandwiched between this interior panel and the exterior panel, we have a sheet of lead that's actually applied to this inner panel. At our joints, we have the same type of overlapping joint, only much tighter, yet again with thick stainless steel and lead lining on the joint covers in here. On our front panel, we have additional lead shielding on this side, covering any area where a direct beam might strike, even some general scatter, higher energy scatter. So our shielding is actually extremely well done. Yet again, no direct path to the outside. The top is removable, but it's interlocked. Going back to shielding, the floor is made of wood, and then the floor of the entire radiation housing is a heavy gauge steel. And then obviously we have the whole housing underneath here, the whole lower housing. However, between the wood and the steel bottom of the radiation housing, we have yet another layer of lead, which wraps all the way around to the edges of the wood. So this is extremely well shielded. The front panel is also lead impregnated glass. These are listed and rated to 110 kV lead impregnated glass. So that's basically the shielding. That's how we can, or that's a good overview of the shielding. Now onto the interlocks. This housing has a front door on a swing, a roof which is removable, and two side panels which are both removable. Every removable panel has dual interlocks on it, 2 switches for each panel. We can see here on the front panel we have these pins. On the side panels we have the same type of pins, both sides. And then inside we have micro switches, and these micro switches are there to, or actually the interlocks. So the pin comes in, as long as the door is closed, both interlocks are satisfied and we can enter X-ray mode. Beyond that, the goniometer itself is positioned inside the radiation housing by 2 brackets. And these brackets each have their own interlock in them. So we have dual interlocks again, ensuring that the goniometer is in the proper position inside of the radiation housing, not leaned forward, not turned sideways. Those feet are ensuring that our goniometer is not in some awkward orientation. The baffle at the rear is a simple 90-degree piece of sheet metal. It lifts up on a hinge, lowers down. When it's in the down position, there are 2 interlocks which are satisfied. One important note about that baffle is that it's relatively common to have someone open it up and get a wire kind of stuck underneath of the edge of it, and that will violate the safety circuit. So that's one of the first places that I'll go to look if we have an open safety circuit on an instrument like this, is to make sure that we don't have a wire under that baffle cover. So that's most of the inside safety circuit. There are a few other aspects related to the shutter that we can go over later. But that's the shielding and the interlocks, the fixed interlocks. Now, we can see up at the very top, we have our X-ray on light. So if we go into X-ray, we have this light up here, as well as our indicator light down here. On most generators, the K710D and older, this is simply an indicator. This light down here is not fail-safe. And that is an important thing to know. On the K760 and newer generators, they have a similar light in the similar position, but it is fail-safe. The K760s added several fail-safe circuits, one of which being this light here. The D5000 has a fail-safe filament light bulb up on top right here. The D500 on its manual control panel has a filament light bulb right here under a cover. Both of them are labeled X-rays on. Now, if these bulbs, if either one of them, or if the fail-safe bulb were to open, the bulb fails, that will violate the safety circuit, just like if we had an interlock switch open. It's exactly the same as far as the instrument is concerned, and it shuts the generator down. One interesting exception, because this is an X-ray diffraction system and we need to gain access to the sample stage, which is in the beam path, regularly. It would be very tedious if we had to shut the generator down all the time. Every time we get in to replace the sample, that wouldn't be very efficient. So what we have is a shutter that blocks off the output of the tube stand. So the shutter is right inside the tube stand before the emission point. It's a simple solenoid actuated gate, effectively, that puts a dense absorber right in front of the emission point of the tube stand. This absorbs all of the X-rays, and nothing is readable out of it. It doesn't leak. And the design is extremely fail-safe. If it gets stuck, and it gets stuck in the open position, we have interlocks to make sure that we don't let the generator come on with a shutter that is open. That's also extremely rare. But this necessitates a complication to the safety circuit. So the rest of the circuit, anytime a panel is off, obviously we want the generator to shut down or at the very least not come on into high voltage mode. So that's fairly simple. The shutter is a complicating factor in that we would like to be able to leave the generator on and open up our glass door at least to change out samples. But we need to ensure that X-rays are being contained in some other area, contained inside of the tube stand while we do that. So the way we do that is, again, the shutter. So the main safety circuit is a simple series circuit, but there is a parallel circuit which is two interlocks on this front glass door right here, as well as the interlocks on the shutter. One or the other must be closed in order for the X-ray safety circuit to be satisfied, or both could be closed, obviously. However, what this gives us the ability to do is we can have our shutter open, collecting data, open the door, change out a sample, close the door, and our shutter can open, all without having to shut the generator down. Now, the X-ray tube on the D5000 also has a set of fail-safe lamps on it. So the shutter itself, the indicator lamps that tell us the shutter is open, are also fail-safe. So it's just yet another layer of protection, and there are two of them. These bulbs fail extremely rarely. They last an extremely long time. But when they do fail, the symptoms are fairly straightforward. Give us a call. We'll talk about it if you think you've got a safety circuit problem. One thing that's important to note is that there are actually 3 switches here on the door. The top 2 are the safety interlock switches, just like any of the other switches on the panels. The lowest switch, you'll notice, is set further back. This is a logic switch. So there are 3 switches that need to be struck. The reason it's set further back is because this sends a signal to the D5000 that the door is being opened, and it needs to close the shutter if the shutter is not already closed. It also tells the logic circuit of the system when the door is closed so that it can open the shutter back up for you for seamless operation. Now, one thing to note is that if we open the door fast enough that we get into a position where the shutter has not closed, but the door is now open. That is, we open it so fast that the shutter doesn't have time to close. Then we have an open shutter and an open door. The safety circuit is violated and the generator shuts off. So I'll demonstrate that by opening the door very quickly. We open the door very quickly. Our safety circuit is violated. The generator shuts off. Likewise, if we were to have, say, the front panel open, we're unable to go into X-ray mode. Note that our indicator light comes on as long as we are pressing the X-ray on button. However, our fail-safe lamp remains off the entire time. So here we are, back to a good operating state. X-rays are on, all of our lamps and lights are working, and we can open our shutter. So it's all very straightforward, very well protected. If you have any questions regarding the safety circuit of these instruments that I haven't gone over, please feel free to give us a call at KS Analytical Systems, 940-453-8786. We're always very happy to talk about particularly Siemens diffractometers, but it's always an interesting conversation when we talk to users. One thing I neglected to mention earlier is that these systems are also equipped with a key switch. This provides managerial control, so the key could be removed and placed in a separate location for control by a manager controlling access to the system. Some states require this type of control. Some corporations have internal regulations that require this type of control. But it is nice to know that it's built into every Siemens generator. Thanks for watching.